What if I told you that within this tiny digital world, evolution is happening in real time? Creatures competing, adapting, and evolving, all driven by natural selection. Welcome to our evolution simulation. For natural selection to work, three conditions must be met. First, there must be a variation in reproductive success. Not every creature gets to pass on its genes. Usually when a creature has higher fitness, it will have higher chances of survival, and over the long run, it is guaranteed to prevail. Second, there must be variation in a trait, like in our simulation, speed or vision of the creature. Third, their trait must have a non-zero correlation with reproductive success. For example, faster creatures may have a better chance at surviving and reproducing. If these conditions are met, natural selection will favor traits that improve survival. Each creature starts with hundreds points of energy. They need to find food to get additional energy and reproduce. Food is limited, so competition is inevitable. Every time a creature moves, it spends energy. So let's run the basic version without any variation in a trait. We start with one creature. Population starts growing at an exponential rate till it reaches its limit because of limited resources. This population stays on the same level over the time. However, there is no variation in speed and vision. This does not allow for natural selection to happen, as our second point is not met. Now we will introduce variation in two traits. First is vision, which explains how far a creature can see. Another one is speed, which explains how fast a creature can move. Every child will have a 10% random chance of either increasing or decreasing these traits. But in evolution, every benefit comes at a cost. Vision is expensive because better eyesight requires more brain power. Speed is costly because faster movements burns more energy. So they're actually rising exponentially. While it may be beneficial to increase them at the start, it may not be so at higher levels, where benefit will not be worth the cost. Like cheetahs evolving speed reaching an astonishing 70 miles per hour. They are not growing further because the benefit of additional speed is not worth the cost. Our traits are predicted to grow up to some level and stop at equilibrium. Let's run the simulation. Species start with reaching its relative population peak due to limited resources. In addition to that, we can see change in vision and speed. By the way, on the bottom right, you can see top 10 dominant species and their count. After 15,000 movements, we can see that our population was established around vision and speed of 14, whereas the dominant species had population of 42. So eventually, our digital ecosystem reaches its equilibrium, a state where creatures have no incentive to deviate to any side, as it is going to decrease their chance of survival. This state is similar to the concept of Nash equilibrium that is used in game theory. A state in which no player can benefit by changing their strategy if others keeps theirs unchanged. It's when creatures' vision and speed traits stabilize, any mutant deviating from this balance gets outcompeted. Let's run the same simulation but reduce exponential cost of speed and check if there are any changes. In this case, we can see, as expected, higher speed was beneficial. However, something weird happened. We didn't change vision cost, but there was a new peak of 20. However, we also had other peaks with vision of 14 and speed of 20. Let's run it again because some things may happen due to random chance. At this time, we had equilibrium around speed of 18 and vision of 10. This may happen due to our huge mutation rate of 10%. To test this concept from the other side, we can start simulation with creatures that have maximum vision and speed and check if they're gonna come to the similar equilibrium. After 40,000 movements, the best species had a vision of 14 and speed of 18, which is around the same result as we got in previous simulation. This result has some variation due to high mutation rate and random chance. But there is much more to explore. In future videos, we'll introduce predators, different survival strategies, and more complex ecosystems. How will evolution play out then?